Okay, today we're looking at 5-2 properties of quadratic function in standard form. We've got two learning targets: define and identify and graph quadratic functions, and identify and use maximums and minimums to solve problems. All right, so we've been looking at quadratic equations in vertex form. Graphed quadratic functions are parabolas that are symmetric, and there is an axis of symmetry. That's a line that you can put down the center through the vertex that cuts the parabola in two halves, two identical or mirror images of each other. So it tells us here that for the quadratic function in vertex form, f of x equals a times x minus h squared plus k, the axis of symmetry is basically at x equals h, because h is where the x coordinate of the vertex, and that goes right through the middle of the parabola. We're going to look at a different form. I guess first we're going to do a problem. Identify the axis of symmetry. So remember, it's a times x minus h plus k. In this case, our h is a -5 since this is positive. So our axis of symmetry is just going to be x equals -5. All right, and you will identify the axis of symmetry for the graph of this function. All right, now we're going to go to standard form. So standard form is probably what we're used to seeing. It's the equation of the form f of x equal ax squared plus bx plus c, where a is not equal to 0. And why can't a be 0? Because if a were 0, the x squared term would go away and we're back to a linear function. This is vertex form. If we FOILed this x minus h squared, distributed the a, we would get to a form that looks like this, and then simplified it. This is standard form. And you can kind of see a is a here, the b is -2ah, and then the c is ah squared plus k. So it kind of shows you from vertex, the stuff in vertex form, where it would end up in standard form. So what are these things? A is still our vertical stretch. By solving for h, we get that h is equal to -b over 2a. And remember, in vertex form, our axis of symmetry is as x equal h. That means in standard form, our axis of symmetry is x equals -b over 2a. C is our y-intercept. We're going to use these to solve problems and graph. Okay, so the properties of a parabola, there's a couple things. Does it open up or down? So this obviously opens up, and one that is opening down would be upside down parabola. It tells us that it opens up if a is positive. So in standard form, if the a is positive, opens up, or down if it's negative. And they have this helpful hint, which I use. If a is positive, you get a smiley face. If a is negative, you get a frowny face, or an upside down parabola. So that makes it easier to remember, I think, whether it's opening up or down. Other properties, as I said, the axis of symmetry is going to be at x equals -b over 2a. The vertex point, this is our x coordinate of the vertex point. How do we find our y coordinate? We're going to plug this value into our equation and solve it, and that's going to give us our y coordinate for our vertex, and then the y-intercept is c. So we'll look at that, doing those things in the next problem. So here's the problem. Consider this function. First thing you want to do is write down your a, b, and c. So here a is 2, b is equal to -4, and c is equal to 5. It says determine whether the graph opens up or down. Remember, a positive, smiley face, a negative, frowny face. Here a is positive, so we have a smiley face, which means it opens upward. Find the axis of symmetry. So it's going to be x at -b over 2a. Since I have my a, b, and c identified, it's going to be a negative of a -4 over 2 times 2. And as they show you, that simplifies down to x equals 1 is our axis of symmetry. All right, this problem continues on. So again, we have a is equal to 2, b is equal to -4, c is equal to 5. Our axis of symmetry was at x equal 1. Now we want to find our vertex. Well, we know our x coordinate's 1. We need our y coordinate. We're going to plug x equal 1 in to our equation for x, as they've done here. And that's going to get us a vertex point y coordinate of 3. So our vertex is 1, 3. And then lastly, y-intercept, easy to identify. It's the only number in the equation without a variable next to it. So 5 is our y-intercept. We're going to use these pieces of information to graph a quadratic function. So we remember we have a vertex at 1, 3, a y-intercept of 5. So we're going to graph the vertex point first at 1, 3. My y-intercept is 5, that's here. And we're going to use the fact that these are symmetric objects or graphs. So I know that if I go in the same number of units in the opposite direction, so I went 1 unit over here to graph this point, I'm going to go 1 unit over here or to the right, and then directly across from this point is another point, and from there I can start to graph my parabola. So those pieces of information makes it much easier to graph parabolas. All right, I have another problem, another example. Here's my function this time. A is equal to, I have a negative in front and no number, so it's -1, B is equal to -2, and C is equal to 3. So upward or downward, A is negative, so we have a frowny face, so it opens downward. Find the axis of symmetry, again, -b over 2a. If we plug them in, we end up with an axis symmetry at -1. And then moving on to find our vertex point, we plug x equal -1 into the equation, as we did here, and we get a vertex -1, 4. And then lastly, our y-intercept is just 3. And again, we'll use those -1, 4 our vertex and y-intercept at 3 to do our graphing. So -1, 4 is our vertex and the y-int at 3. So if I make my vertex point, this is 0, 3. So I'm going to move 1 over in this direction directly across from this point, and now I can draw. And again, since I know it opens downward, I know that helps me check that I actually have made the correct graph. All right, you will do the following: determine whether it opens up or down, find the axis of symmetry, find the vertex, find the y-intercept, and then finally graph this. All right, we also want to use these to find maximum and minimums, and in applications, the maximum or minimum points are pretty useful. So if it opens upward, you're going to get a minimum point. If it opens downward, you're going to get a maximum point. That makes sense. What about domain and range? Domain is always going to be all real numbers because it's going to the graph is going to keep getting bigger and bigger in both directions of x, so there's no restrictions. On y, however, you see if you have a minimum, your vertex is your minimum point. So that means y is going to be greater than or equal to whatever your y-coordinate of your vertex is. If you have a maximum, this is your maximum point, so y has to be less than or equal to that y-coordinate of your vertex. And it's kind of semantics, but when you're asked for a minimum or maximum, we're asking you for the y value of your vertex, not for an ordered pair. We just want the y. The y is considered the maximum or minimum of that function. All right, here's our example. Find the minimum or maximum of the value of the function, then state the domain and range. A is equal to -3, B is equal to 2, C is equal to -4. So we want to, well, first of all, do we have a maximum or minimum? Well, A is less than 0, it's negative, we have a frowny face, so we're going to have a maximum. And then we're going to find it by first finding our x-coordinate of our vertex, -b over 2a. So we plug in our a and b into this and we get 1/3 as our x-coordinate of our vertex. Now we're going to find our maximum by plugging this 1/3 into our x variables in our equation. and they've done that for us here. We end up with a maximum of negative 11 thirds. So note this isn't a large, very large number. The maximum value is negative 11 thirds. Domain is always all real numbers. And remember, when you have a maximum, that's going to be your highest y value. So your range is going to be y such that y is greater than or equal to, or less than or equal to negative 11 thirds. All right, you will do this problem. You find the max or min and state the domain and range. I'm going to look at one application problem quickly. Oops. All right, so the average height in centimeters of a certain type of grain can be modeled by the function h of r. And here it is. R is the distance in centimeters between rows in which the grain is planted, and h is the height. So what's the minimum average height, and what is the row spacing? So we want to figure out the minimum, and we're going to figure out the value of r that gives us that minimum. So we're going to start by finding our a, b, and c, and then plugging that in to find our vertex point, essentially. So the minimum value is going to be at r, h of r. Whoops. It's going to be at this position, and we're going to find r by the row spacing is going to be negative b over 2a, which this is our a, this is our b. So this is the row spacing that gives us the minimum. And now to find the actual minimum, we're going to plug that into our equation right here. And we end up with a height of about 16.5. So that is the minimum height when you plant at this row spacing. All right, I would like you to try this one about highway mileage. You're going to find a maximum, and you're going to use that quadratic function that models it. Write down your questions, and I'll see you next time.